Hello, and welcome to episode 6 of Maths in an Empty Classroom with me, Mr. Southern. Today we're going to be looking at ladder problems, and as the title implies, this is an extension of the work that we did on statics of rigid bodies. So if you haven't looked at lesson 4 and lesson 5 about statics yet, I strongly recommend that you do that before looking at this. Now, when we have a situation where we're modelling a ladder, rather than previously we had a uniform rod resting on a smooth peg, if you have a ladder in contact with a wall, then you have to also consider what's going on at this point where the ladder is in contact with the wall. Generally speaking, we will model the ladder itself as a uniform rod, but because there is contact with the vertical wall, what will happen is we will get a reaction force perpendicular to the wall, where the wall is pushing back on the ladder because the ladder is exerting force on the wall exerts an equal and opposite reaction force on the ladder. So we have two different reaction forces to consider in this model. One is the one exerted by the vertical wall on the ladder, which comes at right angles, and the other reaction force is the one that's exerted by the floor on the ladder at the base, where the ladder is in contact with the floor. Now, the other thing to notice here is the direction that the frictional arrow is drawn. Remember, the point of friction is it opposes motion or the intended direction of motion. Now, if you have a ladder propped up against a wall here, if the ladder were to slip, the way it would go would be like so. It would slip down the wall and the base of the ladder would slip this way. If the base of the ladder is going to slip this way to the right, friction, which is the opposing force, would be going to the left, which is why this frictional arrow has been drawn in this direction. Okay, let's get on and apply this to an example. What I recommend that you do is pause the video, read example 1, have a go at it yourself, because if you've done the statics lessons, you should be in a position where you think, okay, well, it's what I've been doing with one additional force to consider. Let's give it a go. Don't be passive, try and work these things out for yourself. Okay. So pause the video, have a think, and then press go and see if we've got the same. Okay, so a uniform ladder, AB, rests with its top A against a smooth vertical wall and its base B on rough horizontal ground. So straight away again we've got that word smooth and we've got that word rough, which means that the point A, which is at the top against the wall, there is no friction. The point B, which is on the floor, there is friction because it's rough. A mass which is twice the mass of the ladder is attached to the ladder at A, so that's the bit that's up there on the wall. The coefficient of friction between the ladder and the ground is 1/3. Given that the ladder is in limiting equilibrium, just about to slip, find the inclination of the ladder to the horizontal. Right, let's put this into a diagram so that we can work out what's going on. So, we have a smooth wall and we have a rough floor, and then we have a ladder the ladder is in contact with the wall at the point A and in contact with the ground at the point B. And we're being asked to find the angle of inclination, which is that angle theta there. So we'll label that on straight away. That is the end point on our journey. Okay, a mass which is twice the mass of the ladder is attached to the ladder at A. Before we put that on, let's just consider the mass of the ladder itself and where that acts. Because it's uniform, it's going to act in the centre of the ladder. So, approximately there. So I'm going to draw a line straight down that's MG. And as I always do, line in like that, because that angle there is going to be theta as well. Now it's a uniform rod, so this is halfway along the ladder. What we don't know, what we haven't been told, is how long the ladder is. So this is actually something we're just going to have to make up for ourselves. So I'm going to draw a line that's the same length as the ladder along here, and I'm just going to call it A and A, to symbolise that this point here is halfway along the total length of the ladder. Notice I've gone with A and A rather than giving the whole thing a length, because if I'd done that I'd have had to half it and I'd have more fractions in there. I don't want any more fractions, so I've gone with A and A. So I've got that force mg there. I'm then told that there's a force, or a mass, sorry, it's twice the mass of the ladder itself placed at A. So I'm going to draw down here in slightly fatter pen so you can see it over the wall. That force acting downwards there, and that force is 2 mg. Other things that I have to consider. I'm going to have a reaction force at A between the ladder and the wall, so let's label that reaction A. I'm going to have a reaction force at B. Let's call that reaction at B. And I need to consider which direction the friction's going in. Now we talked before that this ladder here, if it was going to slip, it would slip down the wall, causing B to move this way, which means that friction must be acting to the left, opposing the intended direction of motion. So let's get that labelled on there as well. Quick recap of the question to check that I've got all the information forces labelled on the diagram. Top A gets a smooth vertical wall, so I didn't draw any friction in at A. Its base B is on rough horizontal ground, so friction went in there. A mass which is twice the mass of the ladder, I've dealt with that. The one thing that I've missed, coefficient of friction between the ladder and the ground is 1/3. Now what I'm going to do is I'm going to write that in down here, because I know then that it refers to the friction here rather than coefficient of friction here. Although as the wall is smooth there is no friction here, but that's a good long-term strategy. Label that mu at the point where the friction is actually happening. Right, I'm now confident that I've got everything labelled on the diagram that I'm going to need, so let's proceed to answer the question. Given that the ladder is in limiting equilibrium and just about to slip, find the inclination of the ladder to the horizontal. So this is quite tough because we haven't been given any kind of scaffolding in the question, told what to do first, where to go with this. So what we're going to do is we're going to go through our checklist. We're going to do a moments, we're going to resolve vertically, we're going to resolve horizontally, and we're going to see which of those equations gives us what we want to know. So, moments then. In this one, I'm going to take moments about B. And the reason that I'm doing that is I can ignore the reaction at B and I can ignore the friction. Right, so what I need to consider first of all then is that the clockwise moment is going to be equal to the anti-clockwise moment. So what forces do I have that are going to want to make this ladder go in a clockwise direction? And I can see that I've got this reaction at A that's going to be wanting it to turn that way. And I need to consider, okay, what is the perpendicular distance from the point to the line of this force? So what I actually need is this distance here turning like so. So this distance here is going to be 2a sine theta. 2a is my hypotenuse, because it's the length of my whole ladder, and it's sine theta because it's the opposite side. And that is the only force that's causing this to go in a clockwise direction. And that is going to equal 2mg. Now 2mg is going to be multiplied by this length here, which is going to be 2a cos theta. So 2mg times by cos theta. And then this force here, which is going to be mg times by A cos theta. And I've realised there I've missed out my 2A. So let's just fix that. Squeeze that in there, times by 2A for cos theta. Okay. And what I can see here is I've got a few too many unknowns going on. So what I'm going to do is I'm just going to say, okay, the reaction at A times by 2 sine theta is equal to 4 plus 1, 5 mg cos theta. And you'll notice what I've done is cancelled out the a's because they're all the same number. At the moment that isn't helping me find any unknowns, but it will later on, so I'm going to box that so I don't lose it and move on to the next thing, which is to resolve vertically. Now, resolving vertically, I need to consider that all the forces acting up are equal to all the forces acting down. And this is actually quite nice and straightforward because you can see the only force acting vertically upwards is RB, and the only forces acting vertically downwards are 2mg and mg. So I can say that RB is 2mg plus mg